lecture 26. In the last class, we have seen how can we analyze the circuits if the excitation is sinusoidal. That is, if the excitation is sinusoidal and if I am interested only for the steady state response, then what we did, we have studied the phasor approach, that how can we use the phasor approach concept in order to do the analysis of the AC circuits when the excitation is sinusoidal. So we have seen how to compute the voltages and currents for each element. Fine. Also, we have seen the power computation or power calculations in AC circuits. So there we have seen the two types of powers. One was your active or real power, and second was your reactive power. Okay. Active or this was the real power, and the second was your reactive power. So for that we have also seen what is how to compute the active power and reactive power. That was Vi cos theta, and this is nothing but my average power, and this was my Vi sin theta, and mind you, this is not average power, but this is the peak value of the power. As reactive power is that where the load sometimes delivers the power and sometimes absorbs the powers. Okay, and Vi cos theta, that will always deliver the source will deliver the power in this case. And we know what is cos theta, that is power factor, and what is the importance of the power factor, that also we have seen. And we named it real power as P, reactive power as Q. The unit was P for P is the unit for P is watt, and the unit for reactive power was var. Okay. Also we have seen the apparent power, and we have also seen what is the complex power. In order to compute the complex power, what we have to do, Vi complex conjugate, and this has to be done. We have seen why we need to find it out, or why we need to do the Vi asterisk or Vi complex conjugate. Okay, now with this, let us see in this class some numerical examples on the power calculations. That is, say if I have some AC circuit, so for that do the power audit. Okay, do the power audit or do the power analysis. For that, let me draw the circuit. So suppose this is my circuit, which consists of the voltage source, okay, then to this voltage source resistor and a capacitor connected, there resistor and then inductor was there, and again in this branch a resistor and inductor was there. And say this is basically the voltage source, and suppose this is the Vs phasor whose magnitude, any random value, say 108 with 8 degree for example, nothing matters. Then this takes some numbers, so suppose this is 1 ohm, this is minus 1 j ohm, this is 1 ohm, same, this is suppose 1 j ohm, then this is also 1 ohm, and this is 1 j ohm, but 1 j, okay, let me take it this some number here, oh yeah, 3j. Okay, now if I would like to do the power analysis, what should I know? I should know what is the voltage and across, what is the voltage and current for each element. Let us say this is my Z1 bar, this is my Z2 bar, and this is my Z3 bar. Okay, so once I know how much power the source or supply voltage will be delivered, that has to be equal to the sum of the power absorbed by all the impedances, right? So in order to compute that, I know I should know what is the voltage across Z1, Z2, Z3 or current. So in order to do that, first let me calculate the I1 phasor. Suppose let us consider the currents also in each branch. Say this is my I2 phasor, and suppose this is my I3 phasor. Okay. Now to compute I1 phasor for a first example, what we'll do, this we observe that these are in parallel, so we will apply the same, that is to find out the Z equivalent. like what we have done in for the register network. So for that, again, the equivalent circuit I can draw as like this, which will be R C, and this will be R and L. And what is that equivalent value? That I have to find it out. Minus j ohm. This was 108 with 8 degree. Okay. I am interested to compute this I1 phasor. So to obtain this, I observe that Z2 is in parallel with Z3. So what is the Z equivalent? For this Z equivalent for Z2 and Z3. So that is Z2 in parallel with Z3. So it will be Z2 Z3 divided by Z2 bar plus Z3 bar. Okay. So Z2 is suppose 1 plus 3j into 1 plus j and Z2 plus J3, so it will be 2 plus 4j. Okay, 1 and 4j. So if you solve, it comes out to be 3 by 5 as a real part and 4 upon 5 is 4j. J is the imaginary part, which comes out to 0.6 plus 0.5, 0.8j. These are my answers. It may be wrong. You can verify by your own calculations. Okay. Just tell you the procedure, how can we go for the power analysis. Now if I would like to convert it into polar and the rectangular form, this is basically my rectangular form. Its equivalent polar form will be magnitude is 1 with angle 53.13 degree. Okay, so this is now 0.6 with 0.8 j. Okay, now I know this. Next, what I'll do, I'll calculate my I1 phasor. Once I know this, so I1 phasor simply will be V phasor divided by the sum of the impedances. So the equivalent I obtained, it was 1 minus j plus 0.6 minus 0.8 j, which is 108 with 8 degree divided by 1.6. So it is plus, no, plus 0.8j. So 1.6 minus 0.2j. So if I'll convert it into this complex rectangular form, it is coming out 64.67 plus 17.475j, and its equivalent polar form representation is 66.98 with angle 15.121 degree. Okay, so with this now I got it how much is I1 phasor. Now next, to calculate V2, this voltage, this voltage, so I'll call it as V2 phasor, and this is suppose V3 phasor. To compute V2 phasor and V3 phasor, what I need, I can use the voltage divider to find it out, right? So this is overall this voltage only I can call. Okay, so to compute this, V2 phasor will be equal to our total voltage is 108 with angle 8 degree into whatever the voltage for which I've been computing, that is 1 with its polar representation is 1 with 53.13 degree that I have been calculated, divided by addition of this two. So this is addition, I got it as 1.6 minus 0.2j. Okay, so this is 108 with angle 8 degree into 1 with angle 53.13 degree divided by 1.6126 with angle minus 7.12 degree. So this comes out to be how much I got it? It is 66.99 with angle 68.23. This is polar form, and its rectangular form is 24.826 plus 68.221 J volts. Similar, this will be amps. Okay, now I know V2 phasor. Now similarly, once I know the V2 phasor, I can calculate the current through it. So I2 phasor will be V2 phasor divided by Z2 bar, so which is 66.99 into angle 68.23. Recently we have calculated, divided by Z2 bar. Z2 bar means this, which is 1 plus 3J. Okay, so it is 1 plus 3J, and no, yeah, Z2 is 1 plus 3J, so which comes out to be 21.14 minus 1.22J in rectangular form, and in polar form it is 21.175 with angle minus 3.3137 degree. Okay, now I know I2 phasor also. Now I would like to get it I3 phasor. So I don't have to calculate separately voltage because already V2 and V3 have been calculated, and V2 V3 are same. So now I'll write V3 phasor upon Z3 phasor. So V3 phasor is same, 66.96 with angle 68.23 divided by the impedance Z3 bar is 1 plus J, so which is 47.368 with angle 23.24 degree, and its rectangular form is 43.522 plus 18.696 J. Okay, now I know I3 phasor. Now to compute only remains is V1 phasor. Okay, so in order to compute V1 phasor, what is V1? This one will be semi V1 phasors, and this can be, now I know this can be computed as, I know V2 bar and I know the supply voltage. So this V1 can be computed, this minus this voltage. Okay, so to do that, so V1 phasor will be 108 with angle 8 degree supply voltage minus V2 phasor, which we got it as 66.96 with angle 68.23. So plus minus, if I would like to do, you use it the rectangular domain, and multiplication quotient if I would like to compute, better to use the polar form. Okay, so if I will again convert it into this, it is coming in rectangular form is 82.125 minus 47.2J in rectangular form, and in polar form it is 94.717 with angle minus 29.88 degree. Okay, so now I know voltage and current for each and every element in the network. Now what I'll do, I'll check it out for my power balance. Okay, so to do power balance, it should be power delivered by source. So source power delivered which will be equal to the sum of powers absorbed. Okay, sum of power absorbed, and that can be done by this. First calculate source power absorbed. So source power delivered, yeah, power delivered by source will be V phasor into I1 phasor. Okay, and this already computed, 108 angle 8 degree into I1 was 66 point, I have noted down in my paper, so already you can see at the upstream, and you can write it down that 66.98 down with angle 15.121 degree. So if I do the multiplication, it is coming out P in rectangular form 6653.78 plus 2840.542J. So this is my active power, this is my reactive power, and in polar form it is 7233.83 with angle 23.12 degree. Okay. Now sum of power absorbed. Sum of power absorbed all the impedances, which will be V1 phasor, I1 phasor plus V2 phasor, I2 phasor plus V3 phasor, I3 phasor. Now what is V1? It is 94.717 with angle minus 29.89 degree. This is V1 phasor. Into I1 phasor was 66.98 with angle 15.121 plus V2 phasor is 66.99 with angle 68.25 degree. 1 into I2 phasor is 21.175 with angle minus 3.313 degree plus same, that is V3 is same 66.99 with angle 68.25 degree into I3 phasor we obtained as 43.308 with angle 23.24. So if you solve it, the resultant you will get it as 7234.3 angle 23.12, and what is it? It's this domain. Rectangular domain is 6653.2 plus 2840.86 J. So if you compare 7234, here it is 7233. So it is almost same, only maybe the change in the number that been happened because I would have been taken the quantization error. I might have neglected, or I might have round off it. Because of it, it is coming. And 23.12 here also phase is 23.12, and if you compare active and reactive power also 6653, that is coming 6653 and 2840. Okay, this is 2840. So this way you can check it out, the power balance has been there or not. Or also by use of complex power also you can do it. You can calculate the complex power for each, the impedance. So for example, S1 bar, you can correct V1 bar into I1 bar, its complex conjugate. Let me solve for one, which was for impedance Z1 bar. So S1 bar will be, V1 bar is how much? 94.717 into angle minus 29.89 into I1 bar, its complex conjugate. So what is I1 bar? It is 66.98 with complex conjugate. So here it was 15, so it will become minus 15.121. So that way if you calculate it, comes out to be 4486.51 minus 4406.668 J. 4486, this is also same, I got it. Okay, so this way you can calculate, you can obtain for S2 bar, that is for V2 bar into I2 bar, its complex conjugate. Similarly S3 bar, that also you can calculate as I3 complex conjugate. So you will get it 3 complex number, you add it, so we can observe that the addition of all the real powers will be equal to the 6653, and addition of all the imaginary terms, that is the reactive powers, will be 2840.86 J. Okay, so this way we can do the power analysis. So I want to say that here the rules are all will be now same as what we have done for the DC circuits. So there we have, here we have not used any differential or integral equation. If we are interested for the steady state response with sinusoidal excitation using phasor approach. Okay. Now next, just have a quick review on the, or we'll just see how can we again solve the problems for the AC circuit using mesh and nodal analysis. Okay. So just we'll have a quick thing, mesh analysis and nodal analysis. So we know already we have seen for the resistive network. Suppose this is my skeleton. Okay, and there are some source here, some Z1 bar, say here, some Z2 bar, here some Z3 bar, here also some source, some Z4 bar, and let's say here Z5 bar. Okay, so how can you apply the mesh? There will be three independent meshes. This will be I1 mesh current, say this is I2 mesh current, and this is third mesh current. So how can we write the equation? So one side will be the sum of all the sources, and second side will be this the impedance into the current. Okay, so what it will be all the impedances connected in mesh 1, so Z1 bar, Z2 bar into I1 bar, then minus the common impedance between mesh 1 mesh 2, so it is for example Z2, so Z2 bar I2 bar. Again, is there any common impedance between mesh 1 with mesh 3? Yeah, it is there, so it is minus Z1 with I3 bar, and it is equal to all sources, say for example E1 with whatever the angle, like this. Okay, this way we can write for mesh 1, mesh 2, mesh 3. Similarly, what can I write for the node voltages also? Then we can consider say nodal analysis. So one node will be reference node. Select the nodes V1, V2, V3, and suppose I would like to write for the equation for node 1, what it will be? Same, all the sources on right side, and left side will be what? Say the admittances into the node voltages. Okay, so for example 1 over Z1 bar plus 1 over Z2 bar into what it will be, say V1 phasor. Suppose this is my current, or suppose again one more is here, let's say Z0 impedance. So this is Z1 by Z1 plus 1 by Z2 minus common between node 1 and 2. So what is common? 1 over Z1 with V2. Again, is there any common between 1 with 3? Yeah, it is minus 1 upon Z5 bar V3 bar, and is equal to the sources. Suppose this is my source E1 with angle, let's say theta 1 degree. So that can be written as E1 theta 1 degree over Z0 to represent in current form. Okay, so that way you can solve. So just take it some numbers and solve it. So suppose my network is like this, voltage source, then there is a resistor connected, then inductor is there with this one capacitor, and assume that there is current source present. One more branch, let me add there, suppose it's 2 ohm. So this is my 10 angle 0 degree. Say this is 1 ohm resistor, this is plus J minus J 2 ohm. Okay, so solve using mesh and nodal analysis. In order to do that, suppose I would like to calculate this voltage Vx. Okay, so to do that, first let me solve using mesh analysis. Yeah, what is the number? Let us put it 530 degree ampere here, and this is 10 with 0 phase, 0 degree phase. Okay, so let us assume, let us write using mesh. So suppose this is my I1 phasor, this is my I2 phasor, and current is I3 for assumption. Okay, so let me write for mesh 1. So for mesh 1, what it will be? Source is this, so it will be 10 angle 0 degree with sum of all the impedances connected in or present in mesh 1. So what are it? 1 plus J I1 phasor. Then what is the common between 1 with 2? Minus J I2 phasor. What is the common between 1 with mesh 3? Minus 1 I3 phasor. Okay, done. Equation 1. Okay, and for what is the mesh current I2? Yeah, because here already current source present, so no need to compute directly. I can put it I2 phasor will be the reverse of our considered direction, so it will be minus 5 with angle 30 degree ampere. solved for second mesh current. Now for third, what it will be, sum of all these things, so it will be 1 plus 2 minus j I3 bar minus I1 bar, and then plus j I2 bar, right? So plus j I2 bar, I2 bar, which is equal to 0. Okay. So let us solve it in a convenient form. So using equation 1, it will be 1 plus j I1 phasor minus j I2. So j I2 is minus 5 3, so it will be 5 with angle 30 degree into j, okay, minus I3 phasor, which is 10 angle with 0 degree. So if I will solve, it will be what, 1 plus j I1 phasor, j is 90 degrees, so here 5 with angle 120 degree, here constant, so I will shift it on to the right side. Now it will be 1 plus j I1 bar minus I3 bar, which will be equal to 10 with angle 0 degree minus 5 with angle 120 degree due to this addition of this j. Okay, this is equation 1. And suppose now I would like to solve for this equation. Let us call this equation 3. So again 3 will be what? Again, can we solve this? Yeah. So it will be, first let us solve this, minus I1 phasor plus 3 minus j I2 phasor, no, 3 minus j is I3, I3 phasor and j I2, so it is 5 130 degrees, so that I will shift it on the right side, it will become 5 with 120 degree. Okay, so and this will be, okay, now let us write the thing, 1 plus j I1 phasor minus I3 bar, which will be 10 angle 0 minus this. If you solve, its thing is 12.5 minus j 4.38, say equation 1, and if you solve this, it will be minus I1 phasor plus 3 minus j I3 phasor, and which is coming to be minus 6.83 plus j 1.83, equation 2. Okay, now you can use the method by which you can solve it. I can use the method of simultaneous equation, that I can multiply 1 plus j with this, so that this and this will cancel. Okay, let us solve. So this will be 1 plus j I1 minus I3 phasor, which is 12.5 minus j 4.38, and this is minus 1 plus j I1 phasor plus 2 plus 4 plus 2j. If you solve this, 4 plus 2j, that is 1 plus j, you are multiplying to equation 2, right? So 3 minus j into 1 plus j, if you solve, it will be 4 plus 2j I3 phasor and minus 6.83 plus j 1.83 into 1 plus j, it is coming, no, this is resultant I told. Okay, so this factor is coming after multiplying minus 5 with this 5 with 120 degree. Okay, this let us consider right now a. So if I multiply, it will be minus 6.83 plus j 1.83, and suppose this also, let me write how much, minus 2.5 plus j 4.33. Okay, so now this will be cancelled, I1, so you will get it, I3 will be 3 plus 2j I3 bar will be equal to 5.67 minus j 2.5. Okay, and I3 phasor from it will be 5.67 minus j 2.5 divided by 3 plus 2j, and if you solve it will come out as 1.71 with angle minus 57.48 degree amps. Okay, and if you convert it into, no need, if you convert in time domain also, so what will be I3 of t? It will be 1.71 sine of some frequency omega t minus 57.48 degree amps. That way you can write. Right. Similarly, you can put it I1 bar in any of the equations so that you will get it I3 bar. Okay. Now what next I have to do? I have to compute basically Vx bar, this Vx bar, and this will be equal to I3 I know and 2. So that what will be Vx bar? It will be 2 into I3 bar. I3 bar recently we have calculated. Let me write there only. So I3 phasor is 1.7. So Vx phasor is 2 into 1.71 with angle minus 57.48 degree volts, and this is something 3.42. Angle will remain same, 7.48 volts. Okay, and you can convert it into time domain if you want. Right? So this way you can solve for mesh. Now let us solve for nodal, the same equation for the nodal analysis. Take it the same example like this. Say voltage source, then there is a resistor, then inductor, then capacitor, then there was the current source, AC current source, and one more branch with resistor, 2 ohm numerical value we have taken. What is I am interested to get it, this Vx, and these are my polarities. For this is given 10 angle 0 degree. This is 1 ohm, 1j minus j. That's it. No, again any information? No, that's okay. Now if I would like to apply the nodal analysis, I would like to find out the node voltages, right? So what is this? Is suppose my V1 node, V2 node, V3 node, and this is my reference node. So what I will like to do, V1 0, V2 0, V3 0 like this, and we know that now V1 0 there is no element here, so directly V1 0 is, we know it, that is 10 degree 0 degree, 10 with angle 0 degree. So I know V1 bar, no need to write separately. Now let me write for node 2. So what it will be, all the sum of the admittances, right? So it will be 1 over 1 plus 1 over j, and this is plus or minus 1 over j V2 phasor over, then the common element between node 1 with 2 is 1, so it is minus 1 by V1 phasor, then 1 with common 2, node 2 and 3, it is plus minus 1 over j, so it will be 1 over j into V3 phasor. This will be equal to sources connected which are 0, which is 0 here. So this and this will cancel. So what I can directly write here, it is V2 phasor, this is minus 10, so this will be shifted on to the right side, and this will be minus j V3 phasor, which will be equal to 10 with angle 0 degree. This I can call it as equation 1. Now suppose I would like to write for V3 phasor, so what it will be, all the elements connected with V3 node, so it is 1 by 2, and this is minus 1 over j V3 bar, then the element common between 2 and 3 with negative sign, so it will be 1 over j V2 phasor. When the element connected between 3 with node 1 is 1 with minus 1 by 2 V1 phasor, and this is equal to current coming over here, so it will be as what was the call 530 degree amps, so it was 5 with 30 degrees. So if you solve it this, I got it this I got it as minus 2j v2 phasor plus 1 plus 2j v3 phasor, which is equal to 5 angle 30 degree with whatever you know v1, you know it, if you shift it onto the right side it will be 18.66 plus 5g. Okay, this equation 2, and you can solve with the simultaneous equation. So for this 10 it will be 10j. Okay, no, not 10j, it is 10. So the complex number, there is no real number, so there is no imaginary number, it will be only 10. So now next it was minus 2j v2 phasor, that is equation 2, plus 1 plus 2j v3 phasor, which was 18.66 plus 5j. Now to solve it, let me cancel v2j, so multiply this with minus 2j, oh sorry, plus 2j. So if we multiply with plus 2j, it will be 2j v2 phasor minus means it will become 2 v3 phasor, and it will be 10 into 2, so will be 20j, and this will be minus 2j v2 phasor plus 1 plus 2j v3 phasor, it is 18.66 plus 5j. Okay, this will be cancelled, so my v3 phasor will be 18.66 plus 5j, 25, 5 plus 20, 25j over this 2 plus 2j, so it will be 3 plus 2j. Okay, so it is 3 plus 2j, and if you solve, this is v3, so v3 phasor will be in polar form, it is 8.63 in angle 9.57 degree. Okay, so now let us go to circuit. So I know v3 phasor, I know v1 phasor. What will be vx phasor? Vx phasor simply will be the difference between v1 phasor with v3 phasor. Okay, so v1 phasor was 10 and v3 phasor was minus 8.65 with angle 19.57 degree. So if you solve, it will be 3.43 with minus 57.44 degree volts. Okay, which is also same as we obtained using mesh. Okay, so in time domain you can replace by time domain, which will be 3.43 sine some frequency omega t minus 57.44 degree volts. You can calculate that frequency by counting the J and O. Okay, so this way you can solve the circuits using mesh analysis and or nodal analysis if the excitation is sinusoidal, without writing the equation in terms of differential or integral form, right? So this is the essence of the phasor approach, but here only condition is that if you are interested only for the steady state response, then only you can get it. Okay, so this is very easy. So what I want to say is that all the rules which you have been applied for the solution of the DC circuits, the same can be applied for the AC circuits also. Okay, there is absolutely no difference between. For example, if you would like to do the source transformation also, if I have some AC source with this, say, some impedance connected here, Z1 bar, and to this some load is connected between A with B terminal. Okay, so that also say Vs phasor, so that this also you can convert it into current source. This will be by writing this in parallel with Z1 bar. Okay, and then load impedance ZL bar, and what is this value? This will be Vs phasor into Z1 bar. Vs phasor not into, but it will be division. Okay, so this will be Vs phasor Z1. That way also you can compute. Okay, So I want to same rule will be applicable for the AC circuits also. In one last example, suppose the network is this, one circuit to this, what I'll give, let's say current is this and voltage is this V of t. So V of t is, for example, it is 20 cos of 10t minus 40 degree, and say current is 8 sine of 100t plus 15 plus 10 degree. Okay, so for that, find out, determine the network element, or find out that what is the network element. So that how can you compute? You should know, but before going it, just convert it anyone into the same form. So suppose cosine I would like to convert into sine, so this will be 20 sine of 100t plus 50 degree. Okay, so that has been converted into sine. So better it is converted into sine, or you can convert it into cosine. There is as such no rule, 100 plus 10 degree. Okay, so now calculate the phasor. So what is the phasor? V phasor is 20 with angle 50 degree. What is I phasor? I phasor is 8 with angle 10 degree. So what is my impedance? Z bar will be V phasor by I phasor. Okay, which is 20 by 8 with angle 15 by 10, which is 40 degree. So it will be, it comes out 2.5 with 40 degree. Okay, so let us convert this polar into rectangular form. So it is coming 1.91 plus J 1.6 ohm. So it is P8, you can say the plus sign. So what will be, this will be definitely real part is, means there is a resistor, and if sign is plus, then there will be inductance, right? Means the simple form will be series RL. So what will be the element? Element will be series RL, or there will be RLC also. But thing is that your XL should be greater than your XC. That is, inductive reactance must be greater than your capacitive reactance. Then only it will happen. Okay. And what will be the inductance value if that is the case? Then suppose XL I am taking. So XL is 1.6. So omega L is 1.6, right? So L will be 1.6 upon omega. Omega is how much? Here you go to the signal, that is 100. So here you can write L is equal to 1.6 upon 100. So which is 0.16 or 16 millihenry, you can say. Okay. So the inductance will be 16 millihenry. That way you can also compute the network element if you know the voltage and current for this. Okay. So this way you can solve the AC circuits without writing the differential integral equation. So here today I stop. From next class we will start with the mutually coupled circuits or magnetically coupled circuits. Thank you very much.